Good morning, A Science students. It is yet another beautiful day in the Burner Bunker here. So, wherever you are, whenever you are, morning, evening, or night, hey, it's time for another exciting day of science. And if you ever heard Motley Crue before, Mr. Fetterman, who in the world is Motley Crue? Please Google it. It is an appropriately aged band. Anyway, second day, 8.E.1.1, properties of water. I can identify the properties of water that allow it to play a role in all the spheres of Earth. So yesterday we talked about how water is one of the most important things that we've ever run across here on the planet. Without it, we truly would not have the lives that we have here on Earth. Water is one of the only things that naturally occurs in all three states. And the fact that when we started going through it, so we talked about it was polarity, how one side was positive, the other side was negative. This polarity, gave us hydrogen bonds between the water molecules, and the fact that those hydrogen bonds are what makes water do some really, really interesting things. Particularly yesterday, we talked about cohesion, and given that what gives us surface tension. So today we're going to expand on some more capabilities of water. So today we're going to talk about adhesion to start off with. So where do we go, cursor? Of course, the dog starts barking as soon as I start doing this. Hold on a second. Nietzsche! Come here! Adhesion. Otherwise, she would sit up there and bark and bark and bark. And as I found out yesterday, you actually can hear that on the video. So adhesion. Dog, stop. Lay down. So this is going to look like that because adhesion is an actual word. It's another property of water. It is the bonding of a water molecule to another substance. Yesterday we talked about cohesion, and cohesion is the bonding of a water molecule to other water molecules, but today is adhesion. So adhesion is the property, it's the bonding of a water molecule to another substance. So typically we see this when we talk about capillary action. So see something like this where so that water is coming from over here, and the wetness is just going down that paper towel. It's being drawn up out of this one and down into this one. It's almost like there's a pipe between the two. That's the adhesion and the capillary action effect as it draws that material, draws that water out of one into another. We see this is when something looks like this. So when you have say a pipette or a tube, you see this little curve right here where that water is literally sticking to the sides of the little tube. And so again, over here it says Hg, that's mercury, which is what used to be in thermometers, but You see what it looks like at the top of that. It's got a bubble, but it's not adhering to the sides. And again, same thing. This is going down at the sides, so it's not sticking to the side of this little glass tube is sticking in it. But the water, you can see it upticks right there, and it sits in that little curve into it. That's capillary action. So in what you'll see is that, the narrower the tube, the higher you can get the water to kind of climb up that little tube due to the fact that it's sticking to the sides. And that little name of this thing right here, this little curve where it's sticking to the sides, is called the meniscus. You don't have to know that particularly for this class, but that's what the term is, the meniscus. So we see capillary action. Let's call it adhesion. In capillary action, two L's. Very cool. We see adhesion in capillary action, which is water's ability flow against gravity in a narrow space. So adhesion is a property that leads to capillary action. So but adhesion is the fact that it wants the bonding of a water molecule to another substance. Next thing we're talking about, density. Now, density we've talked about before. So density, I want you guys to remember that density is the mass of a substance per unit volume. What does per unit volume mean? Basically, how much stuff's in the side of a space of a given object, of a given thing. So we have how much stuff is in a given space of a given thing. So, well, on Earth, mass is equal to weight. So the standard density of water is 1 gram per milliliter. We say standard because it changes based on temperature, pressure, air pressure, and if there are any things dissolved into so if something's dissolved into it, it will change the density as well. So you got to basically say, when we talk about standard, I mean it's standard temperature and pressure, and the fact that the item we're talking about is pure at that point, it's pure water, it has nothing dissolved into it. So now here's where it gets scientific on us. So we say standard. Somewhere. I'm not staring at my lap. So we say standard, but in scientific, some days I've just got this all together, and other days it just doesn't go well. So we say standard, but in the scientific term, scientific actuality, the density of water is 0.9998395 grams per milliliter at 4 degrees. Can't do degrees. Celsius. But that is so close to 1 that, of course, we go ahead and say 1. Remember when we talked about the, the atomic mass units of protons, neutrons, and electrons, and space space. So protons, weigh just a bit more than 1, and neutrons weigh just a bit less than 1, and electrons basically don't weigh anything, but they do weigh something, but they, in the mass of the atom, that they weigh effectively nothing, comparatively. So we just go ahead and say it's 1 AMU for a proton and just under 1 AMU for a neutron. So this is one of those things for 0.999834, 4 decimal places. I mean, this is 0.99983, which would be 0.998. We rounded down. So that's awfully close to 1. So we'll just go ahead and say 1. So now here's where things start to get interesting with water. As we go below 4 degrees, water starts to become less dense. And this is where water is one of those things that just absolutely breaks some of the rules that everything else follows. So, and the reason in this particular thing is why ice floats. So as things just, as water goes down below 4 degrees, it starts becoming less dense. It becomes, as you go from like 100 degrees down to 4, it becomes more and more dense, colder it gets. That makes sense. Once it's 4 degrees, magic 4 degrees Celsius. Why 4 degrees? Who knows? That's just where it happens. Once you go south, lower than 4 degrees, it starts actually becoming less dense again. And that's why ice floats. But this is one of those things where it's like, well, guess what? This is another one of those things where why water is so critical to actually having life on Earth. Because is this the reason that, when we have a lake or something that freezes in the winter, it freezes from the top down. Because if it froze, if ice was more dense than the liquid water, it would freeze from the bottom up. And if it did that, it would kill all the fish. But as it does, it freezes from the top down. So when this happens, so when things freeze from the top down, that frozen ice actually creates a layer of insulation that kind of insulates the water that's underneath it and gives that water, basically stays liquid, and then the fish get to live. So it is one of those things that it just absolutely a kind of a like, all right, this doesn't make sense, but guess what? It's one of the things that allows us to actually have life here on Earth. Because go back in time, everything lived in the water. If all the water froze when it got cold, not much would have happened with it. Next thing we're going to talk about. So that all relates to the density. And again, density is just how much stuff is jammed in one particular space. I go on to a thing called specific heat. Now, specific heat, it's a very critical, very scientific term. It's the amount of heat, which is just energy, needed to raise the temperature of 1 gram of substance, 1 degree Celsius. Specific heat, the amount of heat, which is, again, just energy, needed to raise the temperature of 1 gram of a substance 1 degree Celsius. Now, again, depending on how dense it is, 1 gram may be a softball size thing, 1 gram may be a sugar cube size thing, 1 gram may be something the size of a BB, depending on the material. So, again, density plays into this because, to the size of the thing that 1 gram actually happens to be. So now, as we say, water has a high specific heat. Which means it takes more energy to increase temperature of water compared to other substances. This property temperature changes close to large bodies of water. So this property is why air temperature changes gradually between seasons in areas that are close to large bodies of water. So if you've got a body of water next to something, and so because of the high specific heat, it takes a long time to heat it up. But then as we go through a summer, and then summer changes to fall, fall changes to winter. So that big body of water now has all this heat that was put into it slowly, raised the temperature of it. And now that thing, because the air temperature falls, land temperature around it falls because we're getting less radiation from the sun, and the season is changing. Well, suddenly that thing now becomes the thing that gives off heat. And so it keeps the air temperature of any place on land that's close to the body of the water from changing as quickly. So it is it's one of these things that, I mean, it's what allows the oceans to affect our weather so much because of how much heat, read energy, that water can absorb. The high heat capacity of the ocean, of water, helps regulate streams of temperature in the environment. So, I mean, it sounds kind of weird, but I mean, it is. It's slow to heat up, it's slow to cool off. Now, scientifically, here's the actual specific heat of the water. It takes 4,000, excuse me, 4 point, Nietzsche, don't you go up there and bark, 4.184. I'm going to check that because I can't read if I actually have a comma there or a period. Before I go giving you wrong information, I'm going to Google it really quickly. So I'm just going to say specific heat of water. Yep, 4.186. That's what I thought. 4.186 joules per gram of mass. Guess what else this actual number is? This is what we refer to as 1 calorie. So the amount of heat / energy it takes to heat up 1 gram of water is 4.186 joules, also known as 1 calorie. Now, unfortunately, so the calorie that you see on the side of your food package is not actually this calorie. So, because gram water is a little bit, and we weigh, kilograms, not grams. So the calories that you see on the side of a package of food are actually kilocalories, 1,000 calories. So, when you talk about this particular calorie, but food calories and this calorie, remember, are different. So anyway, so that is a caffeine, 1 calorie to heat. So think about it this way. So now it takes one all right, so I'm reading the rest of my stuff here and I'm just going, all right, so it takes 4.186 joules so 4,186 joules of energy from heat to heat 1 kilogram of water. 1 gas. It takes 385 joules to heat 1 kilogram of copper, 1 degree Celsius. (385 joules to heat 1 kilogram of copper, 1 degree Celsius. 4,186 joules of energy to heat 1 kilogram of water, 1 degree Celsius. So copper, is a conductor. It's what's in wires. It's what's in. You ever seen copper pots? So it doesn't take much heat to heat it up. Whereas the water that you would put in the pot takes a lot more energy to heat up. So it's just a comparison there, just using copper. So it just shows you how much more heat that water absorbs in its capacity to do things. Last thing we're going to talk about is the heat of vaporization. You're like, Mr. Furman, why is this important? So this heat of vaporization. So again, remember what vaporization is. Vaporization is what? Something transfers from a liquid to a gas. It vaporizes. It's it's phase change. The amount of heat. Again, every time you see heat, energy, energy too. Needed. Turn 1 gram of a liquid into a vapor. Read gas. Without raising temperature of here's where things get kind of weird with science. So the heat of vaporization is the amount of energy, heat energy needed to turn 1 gram of liquid into a vapor without raising the temperature of liquid. So you have to have, in a science lab, you can just imagine this. So you have to have raised the temperature of the liquid up to the point where it's, quote, it's boiling point. Well, again, when you think about boiling water, I mean, how well can you control the temperature of that entire pot of water? So, I mean, you got to realize the conditions it takes to get, these kind of results. The amount of energy taken to turn from 1 gram of liquid right at the boiling point, but not boiling yet, not officially turning to a vapor yet. And then what's the amount of energy that kicks it from there to a vapor without actually changing it? Because then you have to realize you have to take the temperature of the vapor above, that turns into, and realize that, all right, so if I apply this much energy to it, it goes from a liquid to a vapor, but doesn't actually change temperatures. That's pretty precise science if you think about it. When a liquid is at the boiling point, heat of vaporization is the amount of energy needed to get the material from the liquid state now changing its temperature. Water has the highest known heat of vaporization. Get that. Water has the highest known heat of vaporization. The energy it takes to get it from a liquid into a gas, make that phase change, the amount of energy it takes to get that water from a liquid to a gas is the highest known of any materials we know. I mean, that again, I mean, just to have water have that quality, I mean, it's just interesting. I mean, just amazing that it does. And it's this particular thing it's what makes sweating such an efficient cooling process. Because think about it. Your body exudes sweat, pushes water out of, sweat glands on your skin, in your skin, as you, have literally liquid water on the outside of your body because it knows that in order for that water to then evaporate, it takes the heat of your body and makes it evaporate. Well, it takes a ton of heat to turn that water into a gas. So that water turning into a gas off of your body in the form of, from sweating is a incredible, way to get rid of heat. So again, I mean, here's just this magical quality of water that does something for us that is just an amazing thing. So heat or vaporization, the amount of heat energy needed to turn a gram of a liquid into a vapor without raising the temperature of the liquid. So it's basically you're taking a liquid and turning it into a gas. You're evaporating it. So, but that evaporation takes energy. And the heat of vaporization is the energy that it takes to get it from the liquid state to the gas state without raising the temperature. Remember that. Okay. So at the end of another fabulous lesson here on science. Hope you guys enjoyed it. So remember, heat of vaporization, specific heat, density, adhesion, all these things, and the particular properties of water that they represent are things that we need to know. So enjoy the rest of your day. We'll catch up with you when we catch up with you. It's going out music. Maestro.